Our presentation is titled No Frame Left Behind, Single Pass Video Repetitive Action Counting Using State-Space Transformers. So first, we want to introduce to you what repetitive counting means. These are repetitive actions that occur in motion. So for example, this person chopping here, we want to look at how often he actually is doing that repetitive action. It's very different from action recognition because we're not really looking at what he's doing. We want to know how often he's doing it. And we're not really looking at what type or object the thing, it's class agnostic. So our main problem statement is we're looking at how many counts are these repetitive actions in a video. And we're doing it without class labels. So these videos are not labeled, they are just random like objects on there. And we're looking at the video periodicity. So we're looking at these counts in this video. And these videos could be of any length that we're looking at. So why is repetitive counting really hard? So the first thing is when we're looking at a set of frames in a video that we extract, we look at each frame has something that we are concerned about. However, whenever we're getting multiple sample rates, these information could get lost eventually, but that's not really good for repetitive counting because if every information is actually useful for us because we want to know how often these counts actually occur. And it's not like action recognition to say that, okay, this object is located and that's about it. No, we want to know how often these counts are actually occurred. So one of the ideas that we implement is using a temporal self matrix, where initially when we first get this frames that we extract and onto the encoder, we actually put them into a 2D matrix that and arrange them these frames here side by side. And we compare these frames to get the similarity to match these pairs. Then eventually get a single channel of images that we eventually want to predict the number of counts that we're looking at. And this was inspired by the RepNet model that we're actually referring to.
Okay, so I'm going to talk about how other models have solved this issue of repetitive action counting being very temporally fine-grained, and you can't like lazily sample the frames. One way a lot of these previous systems have done it is just use non-overlapping windows of 64 frames, for example. So if the video is 192 frames long, they'll feed in 64 frames, get the periods, then they'll feed in another 64 frames, get the periods, then another 64 frames, get the periods, and they'll concatenate these all together to understand the periodicity of the video. Another way that other systems do it is they'll take multiple sample rates of the video. So for example, it'll take the first 64 frames of the video, and then it'll also speed up the video by 2 and take another 64 frames. And then it'll speed up the video by 3 and take another 64 frames. And then it'll average together their predictions to try and understand exactly what's going on. And it's, in other words, all of these previous systems have very ad hoc ways of solving this this issue where the information within repetitive videos is very dense. They don't really have a unified way of solving this. And this leads to a very interesting issue where if any of these systems want to upgrade to using like a vision transformer, they basically can't. So even at 64 frames, vision transformers are going to become very, very cumbersome. So take example, VIT Tiny 32 by 32 patches, which is literally the smallest version of VIT that's available. And of course, like on a 224 by 224 video, that's 64 times 7 times 7 patches in the output. And you can't use tubes, right? Because we've already shown you that every single frame matters for this problem. So you can't be taking like a slice of the video temporally. You have to get the patches for every frame. So this would result in about 3,100 total tokens. And if you try to do self-attention with all of these tokens, that doesn't even fit on enterprise GPUs. And forget about even longer videos than 64 frames, right? For it's not even close to possible. So initially we tried to solve this this problem by try to just predict the count in a single pass on like a 3D CNN. That didn't really work. We also talked about trying to interpolate missing frames when we like uniformly sampled the video. We randomly initialized frames between the real frames. We tried learning the missing features through a GAN loss, right? This is what we talked about. And this was extremely taxing. It would take days just to train a system that otherwise without this would only take a few hours. And the loss very rarely converged. We had to be very, very particular with hyperparameters to even get any results. So we found something published in NeurIPS 2021 that gave us our solution. And this is structured states sequence models, which I'll refer to as S4. Essentially, similar to self-attention, it models temporal information. It learns 4 matrices, A, B, C, and D. And all states and outputs can be modeled by these 4 matrices. So X refers to the space. So X of T is the state at time step T, and U is the actual signal at time step T. So they claim that any state is the result of the matrix A times the current time step plus the matrix B times the current input signal. And similarly, the next output signal is C times the current state plus D times the current input signal. And essentially using this, you can model both very close range temporal dependencies and long range temporal dependencies the same way that self-attention does. And the original paper proves a very clever matrix decomposition called Hippo that proves that you can learn these 4 matrices and embed them into your input signal, same way as self-attention, and learn these via gradient descent. This brings us to the S4 transformer, which is what our model hinges on. This was introduced actually in CVPR, and it replaces the self-attention in a transformer with this S4 layer. So similarly to a regular transformer, you have one branch of the transformer actually learns this temporal information in the S4 layer, and then both branches are pooled. So you're reducing, we reduce the the number of spatial tokens through this pooling. And then we have this skip connection, same as a regular transformer. Then after you've actually pooled spatial information, you actually reduce the feature size of all of the tokens. So it's a 1-2 punch of
Alec, can you show the cursor? Put a cursor and see where you are.
Do you see it?
Yeah.
Yeah.
Okay.
So after the pooling, the temporal information goes through an MLP, and the skip connection just goes through a linear layer. And these can basically handle arbitrarily long sequences. In the paper, they actually do sequences of like 10,000 frames because the S4 layer is basically linear as opposed to self-attention, which is quadratic. And then they're concatenated together just like a regular transformer. So basically, similar to a transformer, this gives us temporal information between all of our frames.
All right, I'm going to take over from here. Can everyone see my screen?
Yeah.
Okay, so this is going to be our final model, which we implemented. So we start with a uniform sampling of frames from a video. Unless we state otherwise, we're using 64 frames. Then we send each of these frames through a frame encoder.
We just see say our model. Are you showing something? Okay.
Yeah, maybe it's
Connor, share your screen.
I think I am. Let me try it again.
I think you're sharing it. Yeah.
Yeah, let me try it again. All right. See now?
Yeah.
Okay, so we uniform sample the frames, and we send each of these frames through a frame encoder backbone. We try with a ResNet 50 as well as a VIT backbone. Then here's the main portion of our model, which uses the S4 transformers to model the temporal information. So we have 3 layers of S4 transformers. Here, the first dimension is the frames. The second dimension and third dimension are the spatial dimensions. And the last dimension is the number of features. So we first, in the first S4 transformer, we reduced from 4x4 to 3x3 in the spatial dimension with pooling. And again, also reduced the number of features from 2048 to 1024. Similarly, in the next layer, we reduced from 3x3 by 1024 to 2x2 by 512. And in the last layer, we reduced from 2x2 by 512 to 1x1 by 256 features. Then we compute the temporal self-similarity using the negative softmax of the L2 distance. And this results in 2,048 features per frame, which we reduce to 512 to feed into a transformer. So for
can you do it quickly, because I think it's already you guys took quite much time.
Yeah, I'll move along quick.
Mhm.
So after we pass each of these frame encodings through the transformer, we can use a fully connected layer to generate a period length prediction for each individual frame. Then again, the final count can just be generated by taking the number of frames and dividing by the average period length. So, previous models, to do this in a single pass, they were only able to take in small numbers of frames like 64 and repetitively just do 64 frames, 64 frames, and 64 frames and generate multiple predictions that way. But with the S4 transformer, we're able to take in a larger number of frames and retain the more important temporal information. So we can send a large block of frames through the S4 transformers and get a set of small features, but temporally rich features. And then we could send these features again through our counting model to just generate a large number of period length predictions for a long video. And so for our experiments, we do this with the Countix data set, which is a subset of kinetics, and it only includes repetitive motion segments. And one thing it assumes is equal length repetitions for each repetition. And we have counts anywhere from 2 to 73 for our videos. And we use this much for training and this much for validation. And so here we could see the distribution of the counts and the distribution of the resulting period lengths after uniform sampling in our videos. So for evaluation metrics, we use 2 main evaluation metrics, the mean absolute error, MAE, and the off by 1 error, OBO. And here we're going to say that N is the number of videos, C sub I is the predicted count for video I, and L sub I is the true count for video I. Then the MAE is given by this equation. It's just the normalized absolute difference between the true count and the predicted count. Whereas the OBO is going to be a misclassification rate, which says that any sample where the count was off by more than 1 was misclassified. And so for implementation, we're going to use 64 frames unless we state otherwise, an atom optimizer, a batch size of 5, and a learning rate of 6e to the minus 6. And each of our models were trained for about 40 epochs. And Modsam is going to take it from here, I believe.
Right. So I hope you can see my screen.
Yeah, we see it.
Right. So we did a number of experiments, and the first was that we recreated the RepNet model as they hadn't. We met the DeepMind people, and the one that they had released of the key was different than the one that they had published and reported in the paper. We tried to recreate and then model it. The second was we tested multiple models and that were quite unsuccessful to the base model that we have right now. Next, we tried different variations of the S4 transformer. One was with different number of features in the input. And the number of different frames that we fed into the network, they were from 64, 120, 180, and we tried different than all of them. And we also tried a different VIT backbone for instead of the ResNet, we tried VIT just to see how the results vary. So moving on, so the reported RepNet model has a mean absolute error of 0.36 and an OBO of 0.3. The one that we tested and trained upon, to the best of our knowledge, we got a 0.46 MEE and an OBO of 0.5. Then the S4 model with 34 frames, so we got this respective results, and we tested it out with a number of variations. The best from which we got was the 180 frames model, with which we got 0.47 and 0.46 MEE and OBO respectively. We did also an ablation study with the number of features that we were feeding in. So the first one was we reduced it to 256 features from 512, and we were still with some respectable results. We further decreased it to 64 features, and we were still in the same margin of the results. This shows that the state space modeling ability of temporal scale. And lastly, we also tested out one features just for the heck of it, and the results were obviously off. Lastly, when we replaced the backbone with a VIT instead of a ResNet, we got an MEE of 0.53 and 0.45, as Alec explained, due to the complications present. Lastly, the implications from this paper are that we can counting can be done in longer and denser videos, where we have a number of more repetitions and in a single pass instead of multiple passes. And it can be continually improved when we fed a more number of frames. And the spatial pooling retains relevant temporal information on a longer number of frames. Concluding that the straightforward transformer is simply modeling the results and can model the dense sequences where we have more repetitions present. And this can be used in a number of applications in sports analysis, where we identify certain events and how many times they occurred, and anomalies in videos. The last thing, the more number of frames, the more better results we can get, and instead of multiple passes. And we have achieved comparable state-of-the-art results. These are our references. Thank you.
My name is Alejandro, and my group is Brandon, Joshua, and Daquan, and we're doing Vendino self-supervised video action recognition. So our problem definition is that videos are very common on the internet, but not all of them are labeled or annotated. And so we want to efficiently get useful features from a video without labels, using self-supervised distillation, train on downstream tasks. Our approach is to use the Dino training regimen and modify it to work on video. For related works, there's the self-supervised 3D COPNets such as VICC, TCLR, PCL, and there's supervised video transformer, SVT, self-supervised video transformer. It implements Dino for video, and it has results on UCF 101, HMDB51, and Connects 400 SSV2 as well. It was accepted this year in March. As for a method, we implement video Dino with a Vivid Transformer backbone. We adapt vDino to work with the spatial temporal views for the global and local crops. And so how that works is the global crop will be from frame 1 to frame 32, and the local crops would be from frame 1 to frame 16. Second local view would be a F17 to F32. So comparing SVT to our method, SVT is going to keep spatial cropping from Dino. It is going to vary the frame rates of clips from an input video. It's going to have motional correspondent loss, cross-view correspondent loss, and our method is going to redefine global and local views as temporal cropping and have Dino loss on spatial temporal features, as well as we will experiment with spatial tension loss. So in order to facilitate spatial temporal cropping, we construct 3D patches. So how that's done is we get these 16 input frames where each frame is 224 by 224. We apply 3D convolution, 2 by 16 by 16 on each pair of frames. And then we create this 8 by 14 by 14 3D patch for the input. So now I'm going to pass it over to Josh, who's going to talk about spatial loss.
Okay, so for the spatial loss, the original Dino paper compares over all the features between the student and the teacher model. But using videos means that we are comparing the spatial temporal features. But we want to maintain a good spatial features for potential video object detection. Since in Dino, they were able to nearly segment the images with its self-attention maps, we want to try to preserve that ability with our VDino method. And we can do so by comparing similar frames of a video using features from the spatial encoder of Vivid and then passing those to a spatial loss. And the way this would work is that we'd have the global crops and the local crops, which are sent to the teacher and the student, just like in Dino. And then from there, we get the spatial attention maps from the spatial attention portion of Vivid and send that off to a spatial attention loss. And the video features will then be generated to get the spatial temporal loss using Dino's original cross entropy method. And of course, these losses are back propagated through the student only, and the teacher is updated through EMA. For our experiments, we experimented with performance on action recognition using UCF 101, and we pre-trained our VDino method on UCF 101 and fine-tuned with a linear classifier for 100 epochs. We then compared our performance with other state-of-the-art self-supervised video classification methods for task performance, specifically action recognition, as well as a qualitative analysis of our attention maps from the spatial attention method. So for our results, using a Vivid base model with no spatial loss and ImageNet trained on VIT weights, pre-trained with VIT weights, and our model trained on UCF 101 and fine-tuned on 20% of the UCF 101 training set and evaluated on UCF 101 validation set, we were able to achieve a 60% accuracy, which is comparable to some of the other methods that were pre-trained on UCF 101 specifically, although we were not able to exceed SVT, which was trained on Kinetics 400 and managed to achieve a 90.8% accuracy, top 1 accuracy on UCF 101. So looking at the self-attention maps, we have the first 2 frames of an archery video. And because we're using 3D patches, these 2 frames, or using 3D patches, these 2 frames are used in conjunction with one another to generate these spatial self-attention maps. And then we have that one, the middle of the archery video with its self-attention map, and then the final 2 frames with its self-attention map. And we can kind of see that the attention may very well be focused on the point of motion for that particular set of frames. For instance, a lot of the motion is focused up here in the top center left, and then here focused again on the face and a bit on the arm moving. And then since this one is where the archer is notching and drawing the bow, a lot of that attention is focused on the right. Now it's important to note that because this is generated with 2 frames, there might be a bit of difficulty with self-attention to distinguish between those 2 different frames. And it should also be noted that these attention maps were generated with 16 by 16 spatial patch sizes, whereas Dino's self-attention maps were generated with 8 by 8 spatial patch sizes, and therefore were a bit more higher fidelity. And now I'll pass it off to Deng Quan to go over the space-time complexity.
So one of the key drawbacks of our model is that space requirement for running the model on a GPU, because like Dino is a two model system with a multi-crop input, it already requires much more space to use than a regular single model, supervised model. Then since we are using a video, this space capacity is increased by a number of frames in the videos. And because of this, we are only able to load one video at a time in Newton, which do increase our training times. But this complexity is not specific to our model. SVT also has a large space complexity and was only able to use a batch size of 32 cross 4 GPUs and only train for 28 epochs during the pre-text training. It seems that like a multi-crop self-distillation model currently is required too many resources to feasible for most applicants or budgets. And so as I mentioned in last slides of limitation that was the time and space concept complexity, our model require large amounts of memory and time to train. And we did not have the resources to perform the level of training we experience require, which lead us to not able to perform some of the operation we want. And also, we also did not experiment with the pre-training on other large video data sets such as Connect 400, which may likely increase our models performance due to the longer clips and longer a larger video pool. So for the future research could look optimize the performance of this model with respect to their complexity, and also improve spatial attention loss to match the diagnose near to the segment abilities. So in conclusions, we explore a new method for video self-supervision, make use of the transformer and extend them to the video domains. And then we create a new method for spatial attention loss. And lastly, we experiment with a multi-crop for videos. And that's the end of our presentations.
Okay, so we did the perceiverized decision transformer for reinforcement learning. This was Kishore, James, Michael, and myself. Introduction again, reinforcement learning teaches agents how to act in an environment to achieve a goal. For example, Mario can run forward, backwards, and jump in his environment. The state would be the entire current frame of the game. The reward would be formed on the in-game score, the winning condition, or the time taken. Common issues with standard reinforcement learning models is that learning is iterative over random initializations. Typically, you use the full environment, right? Loading the entire dynamic game every time. It's also difficult to learn optimal behaviors given very sparse rewards. You don't know, Mario has to learn how to, say, jump over the pipe in front of him before he can learn how to do anything further in the level. And the architectures are often problem specific and don't translate well to new tasks. So this is the motivation behind our decision transformer. We moved from that online to offline reinforcement learning. So instead of using the entire game, we're going to use a supervised set of training data. This transforms the problem into a sequence, the reinforcement learning into a sequence problem. Below, we'll ask the network, given the current state, maybe some history of past frames, and a desired reward, to return an action or sequence of actions that maximizes, that gets us to this return score. So here you can see we're passing in this case, this is the game Pong. The winning condition is getting a score of 21. We pass in the entire frame into the state encoder, and then we also pass the possible actions that the model can take. And this will output, the action that we want to take, and then every subsequent action after that as we pass the next frame, the next reward, and the next actions in there. So we had started using a 1D environment that we built by hand in order to move over to an image-based data set. We used the Atari DQN data set and the game Breakout. So Breakout's just trying to bounce this ball off of this platform and knock out as many tiles as possible. And your score goes up every time you break a tile. Again, this is an offline data set, and that was built from a well-trained DQ network model, a DQN model. So this data set consists of 500,000 trajectories, which are just sequences of actions, states, and rewards that we'll use for training our supervised solution. And again, this is supervised so that our decision transformer model will learn from these expert trajectories. So these are all solutions that achieve some decent score. In order to evaluate the model, it would run 10 actual games and then average the score over those 10 games to get an indication of how well the model is performing every epoch. So we started by adapting the architecture a little bit. This is very similar to the decision transformer, and I'll point out the differences. We start with our action embedding, our state embedding, and our reward embedding. In our baseline model, we still use the convolutional embeddings to reduce the feature size of the input images down to a manageable vector. We then append the position encodings, and then we break out into different K, Q, and V linear layers. So in this case, K and V were at 128 neurons, and the Q vector was compressed down to 64. So the Q was half the size of K and V in this case. We then implemented the cross attention, which computes the attention between these K, Q, and V tokens, and then pass that through a multi-layer perceptron and repeat this transformer block, I think 5 times, which was kind of the standard that they used as their baseline GPT model. And then all of that is just used to compute the next action. So again, we adopted the perceiver instead of that GPT-2 model to run with different data types and to reduce the memory footprint for longer contexts. The transformer block is repeated, I think it's 5 times for the depth and predicts the next action. In our experiments, we traded 3 settings in this architecture. We did cross attention versus self attention. We did a convolutional encoding versus a linear embedding of the image. And we also traded off embedding sizes of K and V, where Q is always half of K and V. So this is a lot of information to say something pretty simple. On the left is, oh, I'm sorry, on the right actually is the original decision transformer encoder. This is just a convolution ReLU, convolution ReLU, convolution ReLU, and then a fully connected layer that casts it down to 128 by 128. Those 3 layers we just removed as an experiment for encoding as a flat, as a linear layer, which was more perceiver-like. But we did limit the number of neurons to a pretty tight value in order to keep our computations low. So look at some of the results. We'll show, although the mean reward was less stable, we did find that the maximum return was improved by implementing this cross attention mechanism. By casting our input data into a very sparse, low dimensional encoder, which is that just using a linear layer instead of using all the convolutional layers, that definitely failed to produce good results. So look on the left first. Green is our baseline here. This is using the vanilla decision transformer. You can see over all these epochs, this is the return value, which corresponds to the score. So around like 42 here. The maximum score I think was 62, and this is just the mean score returned at that epoch.
It was 57.6 for the baseline.
For the baseline, right? I'm sorry. And the cross attention, our implementation was 62. Sorry. So yeah, the key point to take away here was that we had varied results of the mean game score over the number of epochs, but the maximum score that we were able to reach was actually higher in the cross attention module. Looking at these two in the bottom, this is when we try to flatten the input by removing the convolutional layers and then also increasing that embedding size as well. And those just failed to converge because there was too tight of a bottleneck. And we were just limited by the number of neurons that we could fit in that initial embedding layer. Pretty much just due to memory constraints. Another interesting result was looking at that cross attention result again, where we got that score of 62. If we just extended the context length by 5, looking back at 5 more samples, that was able to explode upwards, and I'll show the numbers for that in a second. On the right, we can see the GPU memory of all of these different models, and this is more important, I think, than the number of parameters, because when we went to, say, the flat linear layer, that has many more parameters than using a few convolutions, but convolutions, I think, are more expensive operation. So you can see our baseline model was taking up the most GPU memory, while our context length 35, by just changing the cross attention mechanism, we're actually able to reduce that GPU memory usage, as well as using the cross attention module with the same context length as the baseline down here. So we were able to drop the memory usage pretty substantially. Again, that would have been decreased if we had been able to see.
So you have only 1 minute left.
Okay. Yep. So we had been able. That would have been reduced a little bit further if we had been able to just use those flattened embeddings, but they didn't produce great results. So just conclusions on our experiments. We achieved a score of 62 just using our cross attention model. We also achieved a score of 79, an average score of 79.8 using both the cross attention model with a longer context. And this is compared to our baseline model, which only produced a maximum score of 57. Now, the paper baseline was a little bit higher. They reported a mean score of 76.9 with a much higher variance. So their max score could be higher than ours. But compared to our baseline, using the same number of epochs that they had specified that we should use, and using all of their code, we only hit 57.6. So I would say that we approached a competitive score, which was approaching what was published in the original paper, and definitely beating our own baseline model. I think that's really it. We had switched over to the game breakout. We had tried it on Hopper before. We're able to replace the GPT backbone, define our cross attention, try new input features, and basically try trading different things like adopting the longer context size, which we saw helped. So yeah, that's it.
Okay. So good afternoon, everyone. Today we are going to present our project on seismic reconstruction Our project title is ZINET, Transformer-Based Seismic Waveform Reconstructor. It is in association with Dr. Joshua Dickey, hashtag. So we are Group D, and we consist of Anshuman, Parth, myself, Abhishek, and Sir. So here is the overall content of our presentation. It consists of introduction, background, related work, model proposed, experiments, results, and evaluation study, and lastly the conclusion. So in introduction, like I would like to mention first, the major problem is the missing elements or the erroneous data points in a data set is a very major problem. And the reconstruction techniques which are available readily are is difficult to implement on seismic waveforms due to very lengthy sequential inputs and many other reasons as well. So keeping that in mind, here we present a model which is purely based on transformer, and it consists of three parts. The first is a time domain encoder, and the second is a frequency domain encoder, and it consists of also a time plus frequency decoder. So the entire thing works like this: is that the input time domain waveform is directly fed to through patch partition to the time domain encoder. For now, for the frequency domain encoder, we need to like take a detour, and for that we first go ahead and process that time domain data using DTFT, which is basically discrete time Fourier transform, and the real values are then converted to complex values. And then using a divider, we basically divide that into imaginary plane and real plane. And then we basically stack them laterally so that we can feed it to, again, a patch partition and then to the frequency domain encoder. And then these two actually have like the features are extracted and fed it to the decoder, and which gives out the reconstructed waveform. And now coming to the background of it, I will be like skimming through it as because we have already discussed this previously, that the data that we have consists of 7,200 total data points. And we plotted a part of it, which looks like this, and a gap of 60 points, which is the second part over here. This is the basic difference between a reconstruction and inpainting is that the reconstruction is getting as close as to the original waveform, and in inpainting it is like like filling the gap with a believable sequence or like as close as possible that it seems real. So now coming on to the related work, it is divided into four parts basically. The first is where we look into transformer and vision, which is basically the recent works that is done in the field of transformers. The second part is the encoder decoder models, from which is actually our model, like the style of this encoder decoder model is our model is inspired from it. And the details of these are given in the report. And the third that we like took a look into it is audio time series reconstruction. The reason behind that is the 1D data, like how they're using the 1D data to reconstruct using a transformer. And then coming on to image imprinting, we explored these variety of like image imprinting models based on transformer, because it is a very similar problem, and we might get some related work from it, and that's all are given in our report. And now coming to the ZINET model, in the model, it is before coming to the exact model, there are few things that we need to cover. So the first is the pre-processing that we did is we upsampled the data by a factor of 2. And then for noise removal, we have used Butterworth bandpass filtering. And then the frequency tokenization, as I have discussed earlier in the overview, I will be like keeping this short. So the discussed time Fourier transform is basically where the real data is converted to the complex data, and using the divider, the complex data is divided into real plane and imaginary plane. And then we use lateral stacking to stack the real plane and the imaginary plane into a real data points. So this particular thing is then fed it to the frequency domain encoder. So now coming to the transformer block, this is a standard chain framework, but in that we actually have implemented 1D patch merging plus patch shifting, along with the height, the width is along the width, but the height is actually fixed. So now I will be handing it over to Parth, and he will be taking it from here.
All right, am I audible?
Yeah, 5 more minutes left. Okay, so
yeah,
just
sure.
keep in mind.
Yeah. Let's just go over the model architecture. One moment, please. Akash, can you mute, please? Yeah. So yeah, let's as Akash has described it in detail, so I won't go over this all over again, and we have also discussed this earlier. So we get an input waveform, we put it through pre-processing, then one goes to the time encoder, the other goes to the frequency encoder. Before going there, we do all the tokenization, which Akash just described. This lower part is the frequency encoder. We get features respectively from both the encoders, which are fused, and once they enter the decoder, they are processed, and we get a reconstructed waveform. So this is the overall architecture of the SciNet model. Moving on, the data set which we use for the experiments, I'll just again skim through this quickly. It was captured by AFTAC. We have had these many training samples, these many testing samples, and all the data was a time series, is like a time series data of 120 seconds interval, and we had randomly generated gaps of 0.5 to 1 second. Also, we have done a mirroring as an augmentation technique. The training details, again, we'll just skim through it. We had a backbone of ImageNet pre-trained SWinty, and optimizer used was AdamW. We trained it for 80 epochs. For the first 50%, we had a constant learning rate of 10⁻³ and then we had a dynamically decreasing. The loss function was MSE, and we trained it on the Newton server, which had these configurations. So the qualitative results, again, as we showed last time, so we had, to describe in short, we had approximately 3 types of results. So first one was that we got a very favorable construction. It was almost able to mimic the actual waveform. The second one was it was like a pattern detected, but it wasn't able to reconstruct it fully. Still, as we can see, they were able to get the same number of peaks. And the third one was no reconstruction. Our model failed to do that, but these type of examples are very few. So moving on, the evaluation matrix. So this is the part which has not been discussed before. So after a lot of analysis and discussion, we zeroed on 6 different evaluation metrics, which we will present our results on. So they are as follows. It's FID, cosine similarity, symmetric mean absolute percentage error, SSIM, mean absolute error, and root mean square error. So the quantitative results which we have got are as follows. So I have the metrics on my leftmost side, and the arrow just indicates how much value of a particular metric should be to be better. So for example, FID, for FID, the lower the better. For example, cosine similarity, the higher the better. So also I should explain what base reference is. Base reference is basically when there is nothing present in the gap. So basically there is an actual real gap. So that's that's the value we'll get of the metric when there's nothing. And Zynet output is obviously our final output. So these are the values which we get. As we can see, FID we are able to reduce very significantly. Cosine similarity increased by quite a lot. Same goes for the other metrics, as when they, for example, SMAPE decreased from 100 to almost 60%. SSIM went on to go up by a lot. And the MAE and RMSE errors also decreased quite significantly. We also performed ablation studies. So the first one was comparing the model without and with frequency. So our initial model consisted of only time series data, or the time encoder. So there was only one encoder. And now we have in the final Zynet model, we have a frequency encoder as well. So if we compare it with and without frequency, we'll see the following results. So we can see that having the frequency encoder does help a lot, because it does improve the performance. The second ablation study was doing the additional training, which I described earlier, with dynamically decreasing learning rate. So initially we trained for only 40 epochs with a constant learning rate, and then we trained with additional 40 epochs with a dynamically decreasing learning rate. Again, as you can see, for every metric, the performance improved. And that shows that additional training was indeed useful. And it also shows that the model might still be converging, and if we train more, there is a possibility to get even better results. The ablation study number 3 was we used a single encoder for time and frequency domain processing. By that I mean that we attempted to go for a lighter model and for reducing complexity. And we input both time and frequency domain data in a single multi-channel encoder. So the 2 channels of frequency and the single channel of time. So all 3 of them, we used a single encoder. Unfortunately, that attempt was unsuccessful, so we are not reporting the evaluation here. In conclusion, we proposed Zynet, a transformer-based architecture for seismic waveform reconstruction. We used a combination of multiple domains of data, namely time and frequency. And we think that that can act as a backbone for generalized waveform reconstruction, like in any domain, not just seismic data. This provides the trick to perform self-attention on complex numbers, which we just did. So that's what our frequency tokenization was all about. And our model did perform satisfactorily on numerous evaluation metrics. For future work, we will focus on jitter-free suppression of steep slope near the gaps edges. So where the gaps end, there might be sudden jumps. So we are trying to reduce that and trying to get a jitter-free output of that from there. Then we have an iterative reconstruction for partially reconstructed sample. That's something we are also trying. Also incorporating a GAN with our Zynet model for refined reconstruction. We actually did try a GAN before, which did not work, but we might attempt to do that again. And finally, we think that this can be generalized to several other vision tasks. And these are our references. Thank you.
We are Group B. We are object detection on point clouds using token mixing and query reuse with Nate, Ryan, myself, and Crystal. So the problem overview is pretty much point clouds, object detection. Think autonomous driving, assisted driving, electric vehicles, using for detect people, vehicles, pedestrians, cyclists, all that sort of thing. And using transform architecture, we're going to detect these 3 objects as you see here. And we are doing it across multiple frames in a video. And essentially, the actual problem itself is the trade-offs of speed, accuracy, and training time. We present that we are going to use a FNet encoder and to reduce the token count. So the related work for this problem is 3DETR is a transformer for end-to-end object detection on point clouds. We are going to use this as our base. And then FNet is sort of what we're implementing to reduce the training time. So we'll use this to change up the encoding, and we'll see that in the next slide. So down below, you'll see 3DETR as our base. This is 3DETR right here. These are the object detections it outputs. And we use the, we modify the transformer encoder right here. And we are going to try, we propose that we either use no encoder or an FNet encoder, which is that mixing sublayer that we talked about previously. And we're going to go more into depth of this architecture with Ryan.
All right. Can you see? Okay.
Yes.
So our basic architecture is the 3DETR. And so this is the transformer architecture. There is an encoder and decoder process. The encoder is just the normal transformer. We've got multi-head attention. And then the decoder is a normal transformer decoder with, again, some more multi-headed attentions. We will be messing with the encoder in this project. We're not going to do anything to the decoder. This will remain the same through all of our different architectures. The default configuration is 3 of these encoders stacked. And that is that baseline. Then we're also trying out 2 variations to try and increase speed while maintaining performance. So the first one is no encoder, which we just implemented by making something that would just pass the tokens along, and that was just for ease of implementation. And the point of this is to get a baseline. Ideally, something with an encoder would have the highest accuracy and something without an encoder would have the lowest accuracy. So that way we can see where FNet ranks between the 2. Then we also have the FNet version of this process where it's very similar to the transformer encoder with a couple minor modifications around where adding a normalization takes place and the number of times. And then the multi-hit attention is replaced with this Fourier transform. And something important to note with the Fourier transform is it must be done an even number of times or else it will adversely affect performance. And so we had to stray from the default configuration of 3DETR, which was 3 encoders for the FNet model, and use 4 encoders. And as a review of FNet from last time, so the Fourier transform is a signal processing technique. That's where it's usually used. The previous group mentioned they used it for signal processing. You can also use it for different embeddings. We're using it for as a replacement for the attention mechanism. So we're going to mix tokens together instead of doing the attention. And so the FNet encoder uses a Fourier mixing sublayer instead of the attention, that multi-head attention sublayer. This works by first doing a discrete Fourier transform along the hidden dimension, which you can see here, and then doing it along the sequence dimension, and then only take their real values. And even though that's a bit weird, it turns out not to have an adverse effect on performance. And so the whole idea of this FNet thing is it's going to reduce the compute, particularly the memory burden of like a regular transformer, without severely impacting accuracy. And as a frame of reference, we go from the token being n squared to the Fourier process being n log n. And now I will pass it to Nate.
Can you see my screen?
Yes. Okay.
So the second part of our project is query point reuse. So just as kind of an overview of how that works, as background, 3DETR in its decoder uses seed points, much like DDETR, to make object detections. It will look at those points to try to generate a box, and that will either have a classification or a no class label. And the no class labels are thrown away, and then the resulting classifications are the detections that the model makes. So what we did was to kind of leverage the fact that the decoder outputs the centers of these, the normalized centers of these prediction boxes. And we take those from the previous frame and we pass it into the next frame, into the query points of the next frame. And that replaces one of the randomly sampled query points that the decoder normally uses. And effectively, the intuition for this mechanism is that we're kind of forcing the model to look in the same place that it already found something with a high degree of confidence and redetect that object. So this can be used for 2 things. We wanted to use it for multi-object tracking in point clouds. I'm going to go into why we couldn't evaluate that in one of the next slides, but it can also be used to find similar objects that are in a similar location and pose in different frames. So here, I'm going to show some qualitative results that we've generated. So this video is of a car driving down the road, and you can see on the left-hand side, there were a lot of points that were red, and those red points are reused object queries. And a lot of the times they're picking up the same object and redetecting it, and that could be used for tracking, but it's also kind of showing that we can look in that same spot for similar objects, and those are cars just parked on the side of the street, so it's helping to detect more of the cars. So as far as the results and the challenges on the tracking, like I said, our current results are only qualitative, and I'm going to go into that for a second, or in a second. But the video clearly illustrates that points are being reused and objects are being redetected across the frame, as we just showed. And something that we were able to measure is that more than half of the reused query points do result in a re-identification of the object. So that's not just detecting a new object, it's actually kind of effectively tracking the same object across frames. And we found also that, like I said, query reuse can also help to find objects that are kind of spaced out regularly in a pattern in the same area of the point cloud. Some of the challenges that we faced were that we couldn't get metrics on tracking because the data set that we were using heavily, Kitty, only provides tracking labels for 2D images. So it's just video tracking. Given more time, potentially what we could do is we could take these, since they're in the camera's view and we crop to camera view space in 3D, we could potentially project these track points to the Velodyne coordinate space and generate those centers so that we could track the track IDs. But we didn't have enough time. We came up with this concept right before project update 2. So that would allow us to evaluate our tracking performance. And we could also explore more 3D video data sets that do actually have tracking ground truth labels for point cloud videos. So I'm going to pass it over to Crystal to discuss some of our other results and experiments.
Okay, so as a quick overview, the 2 data sets we used are Kitty and SunRGBD. Kitty has about 80,000 3D annotated bounding box, whereas SunRGBD has about 58,000. We use SunRGBD as a point of comparison because this is what the original 3-detter used. For our experiments and results, all of them had the query point set to 256, and all of the hyperparameters were set to the same thing that 3-detter used on SunRGBD to keep the models consistent. On Kitty, we trained for as many epochs as possible over the course of about 4 days. That was about 440 epochs for 3-detter and no encoder, and only about 280 epochs for FNet because we encountered an error and had to restart the training about halfway through. On SunRGBD, we trained the model for 4 days, and all of them were trained for 1080 epochs. So as a quick comparison on SunRGBD, all of the models performed about the same with a mean average precision of about 57, which is comparable to VoteNet, which something that 3-detter did use. It outperformed BoxNet, but it's not the state of the art. It does not outperform HGNet. And this is true for all of these different classes. On Kitty, again, this is where FNet was trained for 160 fewer epochs. However, we can see that the performance is actually still fairly comparable, and it would likely share the same results that we saw previously. And even though it was trained for 160 fewer epochs, we still see some good results with like cyclists. For training and inference time, 3-detter with no encoder did reduce the training time by about 18% on SunRGBD, and using the FNet encoder reduced the training time by about 11%. For the inference time, we didn't find that there was a large difference between the different models because it varied quite significantly between inference runs, but it was pretty consistent. In general, no encoder was faster. FNet was right in between 3-DETR and no encoder. So another thing we wanted to look at was the impact of the number of query points. 3-DETR reported that the AP25 decreased with the number of queries going above 384. We found that not necessarily the case, and it can be an area of future study. This is the chart from 3-DETR when they increased the number of queries from 256 to 384. They actually saw it either stayed the same or went down in MAP. But we found that in the case of Kitty without view cropping, that the query capacity and the number of query points was very important. 3-DETR actually ran out of memory at 512, but FNet and no encoder both greatly increased in accuracy in MAP, sorry. And this is something that should be maybe studied in the future. Basically, it seems like the number of points is relative to the size of the image. So in conclusion, reused object queries can be a valuable way to track objects from point clouds. Future experiments would evaluate that tracking performance. And in the case of 3-DETR on the Kitty data set, we found that the encoder was not very important, that removing it reduced the training time and didn't affect the accuracy very much. We found that the FNet encoder did maintain the mean average precision and reduce the training time, but that removing the encoder entirely was more beneficial. And again, the ideal number of object queries can be researched in the future.
So we're Group F, comprised of myself, George, Fernando, and Sarah. And we're going to be talking about taking a page from the VAE codebook, an approach for zero-shot learning on multiple choice visual question answering. So first, I just want to point out some works that kind of contributed to our research. Swen, Bert, and a lot of these we've covered before, so I'm not going to explain them. VQA, I'm assuming most of us know what visual question answering is. The DVAE, or discrete variational autoencoder from Dolly, where we use vector quantization to learn a codebook using assignment based from a softmax distribution. There's a paper in 2016 that addresses zero-shot multiple choice visual question answering. A more recent one that was accepted in ISWC in 2021 that also addresses zero-shot visual question answering using knowledge graphs. And a more recent paper that was accepted in the CVPR 2022 conference, where the task is zero-shot video question answering, where the authors found that a zero-shot multiple choice VQA, so exactly our problem, was used as a pre-training objective for a downstream task of video question answering. And one thing to note here is that the authors found that multiple choice, zero-shot multiple choice specifically, contributed to their downstream performance when compared to no pre-training objective and even an open-ended question answering setting. So next, I'm gonna just briefly describe the problem in the data set. Multiple choice visual question answering is just as it sounds. We attempt to predict a correct answer to a question about a particular image from a predefined list of answers. We use the VQA2 data set, which contains obviously a set of images, questions, and answers. So here we can see some examples. We have this image of Darth Vader with the following questions. Is it raining? What's funny about the Darth Vader character? What color is the umbrella? And is the bear alive? VQA2 is not inherently a multiple choice data set. So in order to generate multiple choice answers, we obviously always include the correct answer that's given by the data set. And to get the 3 remaining answer choices, we organize questions by type, such as like what color questions, or how many, or yes or no type questions. So we organize the questions by that type, and we sample them and grab answer choices from that same question type to kind of build up this list of incorrect answers. To generate our 0-shot data set, we started with, again, the standard VQA2 data set, and we randomly chose words to remove, and then we parsed the list of questions and answers to check for a matching substring. And then we just remove that instance from the training data set and move that to validation. So really quickly, I just want to draw your attention to these 2 red boxes, since they're pretty much the most important here. Obviously, in the training data set, there's going to be no instances of 1 or more unseen words. But when we look at the 0-shot test data set, we can see that every single instance here has at least 1 or more unseen words. And these are kind of broken down into categories here. So there's instances with 1 or more unseen words in questions and images in the correct answer, and also in the answer choices. One quick thing to note is in images, an unseen word in an image means that we're essentially removing instances of questions that share an image ID. So for example, if we chose the word rain to remove or raining to remove, this image ID is going to be associated with these instances of these questions, and they're also going to be removed from training and sent to the validation set. So I know that unseen words and images can be a little confusing, so I thought it was important to clarify that. Next, I'm going to quickly explain our architecture in reverse order from the paper, because it makes more sense that way. So in B, we can see a vector quantized transformer here, where we essentially just utilize a SWIN or a BERT, depending on the input that we're getting, to produce a matrix of latent features, which we use to learn a code book in a very similar fashion used in DALL-E. Each of the image, question, and answer tokens go through this process to produce their own matrix here. So knowing this, the proposed Zesty VQA architecture builds matrices of these latent features produced by these vector quantized transformers from the tokenized input images and text. Next, the image and question matrices are passed into a transformer decoder whose output is then used along with the answer feature matrix as the input to our final transformer decoder. The final transformer decoder just performs cross attention on the image, question, text, and answer text features, and feeds its output to a multi-layer perceptron. And I think we know the rest of the story here. This is how we get our answers.
So this figure you made yourself, or you cut from some paper?
I did make this, and I also this is a figure from our paper, and of course I just kind of cut it to maybe try and make more sense for a presentation setting.
Good.
So the next question somebody might be asking is, why use a code book? So learning a code book allows us to discretize the input image and text feature representations. The motivation behind this is the expectation that the model can use context around the unseen data to assign a codebook vector that most closely represents the features. Since we've seen good performance in a 0-shot generative setting like DALL-E, we thought maybe those strengths could transfer well to our application. So for example, let's say these red dots are our codebook vectors, and we get a feature representation, say this green dot. If our green dot is a feature representation of our input, discrete assignment allows us to kind of just assign this guy to our closest one. our closest codebook vector here. So another advantage of this is that codebooks kind of give us control over how specific we want our feature representation to be. So for example, a large codebook can represent very specific features. Like if we have a bunch of these kind of red dots that represent a vector in our codebook, and we have a lot of them, we can represent rich features like textures and things like that. Whereas if we have a smaller codebook, it might only represent very generic features, maybe like color or something like that. And we have control over this element versus like a k nearest neighbor kind of thing where we have to store the entire data set. And next I'm going to pass it off to Fernando to go over our results.
Now for our updated result, we were able to train all the models on the Newton cluster, and this is what we got. First, just to set a baseline, a randomly guessing an answer should achieve a 25% of guessing right, regardless of the data set. For the upper bound of the accuracy, a human can achieve above 95% on normal and zero shot. Then for the CNN plus LSTM counterpart of our project, our model achieved 57.2% in a standard split, while it only reached 52.7% for the zero shot split. And finally, for our transformer, we achieve an accuracy of 63.4 in a standard split and 60.1 for the zero shot split. In addition, the codebook did improve the standard split accuracy by 0.3% and the zero shot all by 1.4%. And the zero shot questions got the best performance with a 62.3 accuracy, 49%, 49.9% for the zero shot answers, and 42.7 for the zero shot choices. Okay. We also analyzed the performance on each of the question types labeled by the BQA dataset to understand what the model's weaknesses and strengths are. Each question type has been listed on the left with their corresponding phrase. For example, the one highlighted in red is a what room is type of question, which will include a question like what room is this? And the answer could be like entry room or kitchen. The two bars next to the question type are the percentage of correctly answered in blue and incorrectly answered on green. That side. For example, for the what room is type, it achieved in 88.89% accuracy. So these are the question types that their corresponding accuracies. The biggest takeaway of this figure is that the model had good performance on what or where type of questions, where the questions directly address an object that can likely be seen in the given image, which is to be expected. And as we were expecting, the model struggled with questions that require a higher level of understanding of the scene. For instance, the how, who, why, what brand, those type of questions. With this in mind, we added the codebook to the transformer to see if that could help discretize the given image and the text feature representations and gain an edge over the difficult questions by decoding on continuous feature representations to see if it will improve the decoding process and if it will get better features from the image. But unfortunately, the codebook showed the same weaknesses, but it achieved an overall better result. We speculate that if we were to pre-train our decoders for a panoptic segmentation task, the model might be able to improve the accuracies on the high-level questions, but that will be for future work. Then Another analysis that we did was to measure the per question length accuracy. The y-axis is the number of questions, and the x-axis is the actual question length. To make this more readable, we separated the length in bins of 5. So for these results, we can see how questions 55 to 60 characters and less than 20 characters contain the biggest percentage of failure, with 51.16 and 55% accuracy respectively. This could mean that either too little information was given to the model to correctly choose an answer, or too many irrelevant words were given to the model and confused some activation layers. However, questions with character length of 60 or more performed the best with 66% accuracy, but we believe this might be an outlier since we didn't have that many questions with that length. Another thing to note is that even though most of the data set was formed with questions between 25 and 40, the model was able to generalize and kept the accuracy stable across the other ranges with about 61% accuracy. And finally, for our conclusion, we saw that our zero-shot transformer VQA plus codebook achieved promising results against state-of-the-art methods. Codebooks are a good way to improve performance when a discrete representation of a problem is needed. We believe that zero-shot learning should be normalized and something to do more frequently on machine learning problems. It just makes sense. More believable results, since these methods are supposed to be used in the real world with unseen data. So we kind of want to emphasize to normalize them. And lastly, we confirm the fact that semantic questions are the main reason of PQA models performing way below the human level. And if we really want to progress in this field, we need to address this issue. And here are the references. Thank you.
So our project for the class was Tiny Action Recognition Challenge, which is part of ActivityNet workshop held in CVPR this year. So our team members are Mehdi, me, Sanjay, Kasun, and Dane. So we're going to go over the problem statement, the main proposed method, some ideas along the feature engineering pipeline that we tried, future work, followed by conclusion. So the problem statement is pretty straightforward. We have to perform action recognition or video classification on low resolution video dataset, which is Tiny Virat video dataset, which is part of Tiny Action Challenge of CVPR 2022 this year. So the challenge have two tasks, detection and recognition, and we are focusing on activity recognition, which is basically a multi-label video classification task for the challenge dataset. So here is a sample from the Tiny Virat dataset, which is a low resolution video. So our proposed method is an adversarial super resolution pipeline, which is our basic first pipeline that we started off with. And we experimented with this pipeline with few variations in it. So I'll quickly go over the high level flow of the pipeline. We start off with a pre-trained video swing network, which is pre-trained on a high resolution data set like Kinetics 400. And we take a student video classification network like VideoSwin or Vivid. We pass a high resolution video from Kinetics dataset to this VideoSwin network to get an embedding. And we pass a low resolution video sample from Tiny Virat to the student network to get its embedding. And we make sure that the label of the video sample that we are taking from Tiny Virat is similar to the label of the sample that we are getting from the high resolution dataset. We append the label with these embeddings and we pass it to a discriminator to allow it to tell apart the high resolution embedding from low resolution embeddings. And we train the student network using a binary cross entropy loss. So the results that we got using this basic pipeline, first off, we tried a simple video vision transformer vivid network on the tiny action, the tiny Virat data set, and that gave us an F1 score of around 8% on the test data set after we submitted it to the evaluation server of the competition. Then we switched to a video swin, a pre-trained video swin, which was pre-trained on Kinetics 400. We fine-tuned this video swin on the Tiny Action Recognition Challenge competitions data set. And that gave us like slight improvement over Vivid. And that is proven from the literature as well, because over the high resolution data sets too, video swin outperforms Vivid. So we saw that pattern in low resolution video classification as well. As for the adversarial pipeline that we have proposed, when we took the student network as vivid and we used the KL divergence loss, we got an F1 score of 12%, which was a significant improvement over vanilla video classification transformers. And when we changed the training setting for this network a little bit with gradient penalty and Wasser's team loss, we saw a little bit improvement in the F1 scores. Then in order to boost these scores a little bit more, we experimented around with this architecture. And since the teacher was a video swin network, we assumed that a student should have an equal amount of learning capacity to make this framework perform well. So we made the student network a video swin as well. So that gave us an improvement of almost 1% in our F1 score. And then with a better training setup, we got the best F1 score of 14%. So this was the best F1 score that we got so far. The top score on the leaderboard right now is way high as compared to what we are getting. It's around 46%. And the best convolutional baseline network that is proposed by UCF, the competition organizers, is 32%, which is a R2 plus 1D convolutional video classification network. So we plan to improve this F1 score to at least cross the baseline by using a modified and a slightly improved version of this framework, which we call quantized adversarial super resolution network. But we came up with this idea for like 2 weeks ago after project update 2 a while ago. So it's a big pipeline and we're still implementing it. So we don't have results for this yet, but I can quickly go over the idea of how we plan to improve this framework. So this is our improved final quantized adversarial super resolution framework that we plan to use for the Tiny Action Recognition Challenge. So we actually, this is not supposed to be here, so I can just remove it for now. So we start off with a kinetics data set, and this framework is inspired from the VQ-GAN architecture. So we convert kinetics videos to frames, and we only choose those video samples which are from the Tiny Virat labels, which have the action labels like of Tiny Virat. So we convert kinetics videos to frames and we pass it through a 2D CNN encoder like ResNet 50, which maps the frames to a latent space, which is then quantized using the closest vectors from a fixed size codebook. This quantized feature representation is then passed to a 2D CNN decoder, which tries to reconstruct the original frame. And then we have a discriminator, which tries to tell the original frame from the reconstructed frame apart. So after this pipeline, we train a code book, which comprises of visual code words of kinetics, a high resolution data set. So what we actually do is that we discard the discriminator and encoder, and we follow the same pipeline, but this time for the Tiny Virat data set. So we pass the Tiny Virat samples through a CNN encoder, and we use the Kinetics 400 codebook to represent Tiny Virat frames using a Kinetics 400 codebook. Then we use that quantized feature representation to reconstruct Tiny Virat frames, and the discriminator tries to tell the reconstructed frames apart from the original one. And the idea of this whole pipeline is to kind of map low resolution tiny Virat samples using a Kinetics 400 codebook into a better high resolution feature space. So ultimately, once we are done, we use this VAE pipeline, this variational autoencoder pipeline, to project tiny Virat videos to a higher resolution. And those high resolution videos can then be passed to any video classification network like Vivid or VideoSwin for getting final class labels. So that's that. And I'm going to pass it on to Dane to talk about some feature engineering experiments that we did.
Okay, you guys see my screen? Awesome. So basically, I'm going to talk over some feature engineering experiments that we ran. So first one of them was the idea that there's, if you look at some of the samples of the tiny Virat data set, this is a good example where you see the environment and how it moves and sort of shakes and jitters. So one idea was to kind of apply a sort of corrective camera tracking idea. So the idea behind that is to, once we get this information, it's both corrective, as if you think of this video in tubelets, those tubelets actually kind of shear across the time dimension because they move. And then this is also informative because it tells us, hey, the camera's moving, so it's likely more of a walking action or a vehicle action as opposed to stationary action. So we can get this information simply by minimizing the difference between shifted frames, and then
so you have only 2 minutes left, so you can try to wrap it up. Okay.
Okay. Well, then in short, we tried camera checking methods, and we also tried pose tracking methods. The pose tracking was done through a separate Vivid-based transformer with multiple poses if there are multiple actors in the scene. The camera tracking gave us a slight improvement, which is great. The pose tracking on its own didn't have enough information to give us significant results, but they are there. So this could be a good enhancement to existing methods. So overall, the best method is still the adversarial. And with that, I'll pass it on to Sanjay.
I hope I'm audible.
Yes.
So I'll be talking about the future work. So apart from the method mentioned by Momal, that is the quantized adversarial super resolution, we also plan to work on the unsupervised super resolution, wherein we try to remove the dependency of the low resolution, high resolution pair that is required by the super resolution. So here we want to use the unsupervised pipeline. And this is how the working pipeline looks like. The first part in the pipeline is a data creation pipeline, wherein we use a kernel GAN called as blind SR kernel GAN, whose task is to estimate the noise component in the low resolution image videos or the data. So what we do is we just pass the tiny Virat low resolution videos through the blind SR kernel GAN, and it estimates the noise component of the videos. Once the all of the tiny Virat videos are passed through the video kernel GAN, we get a pool of low resolution kernels. And once these are obtained, we try to pass the Kinetics 400 high resolution videos through the kernel GAN and generate low resolution videos.
So you guys haven't done all this. Is that just
the future work? Yeah, future work.
I think you can just end it here. Okay, just because that's fine. I got an idea.
Okay.
Do you have more slides? Just quickly go through.
Yes, Professor. I'll just try to conclude this.
The project was what you have done. You talk about that, not what you could do. Today is a final exam.
Okay.
Okay. Yeah. Conclude.
This slide is the only slide we did not do, and the quantized.
Yeah. So followed by data creation pipeline, we have a training pipeline which uses the same adversarial approach to train using the low resolution videos generated by the data creation. And once that is done, we use it for the inferencing, wherein we pass the tiny VRAT videos and generate the high resolution data. So this was all about the unsupervised super resolution method. And I'd like to conclude by saying that adversarial super resolution actually increased performance as compared to the transformer video classification baselines, as it was evident in the results. And we also noticed that convolutional video classification networks works better as compared to SOTA transformer networks on video classification. And finally, we also tried feature engineering on low resolution videos, but it didn't give us like much significant improvement in terms of the accuracy. And finally, we also proposed a quantized adversarial supervision approach, and we are still working on that.
That one's currently in training, by the way, too. So that one's implemented.
Okay, thank you very much.
Yeah, the
Let's go to
references.
the next
Thank
one.
you.
So the group H, composed of Jacob, Sharon, Jacob P, and myself, Tristan. Our project was using transformer for our data set, which is we have to perform instant segmentation on images of cells, where the two main challenges are that we have some very small objects with high number of objects per image, and we have a small training data set. So as seen before, this is the image. We have small cells and we have around 600 per image. Then our training data is relatively low with 46 images, and we're dealing with imaging mass cytometry. So the method we use is a refined mass transformer approach, which we adapted to small objects with local dependencies, because the cell here is not going to rely on something like this. It's only going to rely on the local information. And we have this low training data. So before this project, as a comparison model, we have a Moscow CNN that was run on this data set. So if you have the ground truth that's here are the results we're getting. So you can see that the cells are almost all detected. However, the area is really not the same. So AP scores were around 53%, with 60% of the cells having above 50% AP, but only 6% having above 75 IOU score. And then we have our true positive F1 recall and stuff like that, where we don't have a lot of false positives because we're not detecting cells that don't exist, but we're missing a few cells, so our recall is a little bit lower than our precision. Now to go into our actual implementation of the refined mass transformer, what we did is we transform our data set into a COCO format, and then we started modifying the different aspects that we wanted to do. The problem is when we run the model, on the change mass transformer based on local attention, but also on the original one, it was the same problem. It wasn't able to perform because of the small data set, which meant that whatever we did, the model returned us empty bounding boxes with score zeros. So we had n empty bounding boxes, which was no position, no size, and we had n, which is the number of queries. So we had n empty bounding boxes. The reason it failed is mostly due to the large amount of data that's needed for transformers, while convolution, like the Moscow CNN, was able to perform because they converge faster than transformers. We couldn't get the transformer method to converge. The reason for that is mainly because instant segmentation is a very difficult task for computer vision, because we need bounding box refinements and segmentation. So that needs even more training data, and also the mass transformer is built on DTR, which is the deformable attention. Deformable attention. So the high number of instances wasn't helping. We tried to solve that problem of high number of instances because we would use random crop size. So we would make the image much smaller, but that didn't solve the problem of the model not converging. So we tried a lot of different things like lower encoder layers, lower convolution layers, lower queries, different data augmentations, batch size, learning size. We tried all that, but it wasn't converging still. So that's our approach. We want to talk more about the modifications to the method we made because we think it's really applicable to that kind of data. It's more of if from this technology we had a lot more training data, I think there's really something to do, but we couldn't do it for now because we don't have that high amount of training data. So I'll pass it on to Jacob.
So we originally started off with the Mass2 former because the Mass2 former performs very well in instant segmentation, and because it used mass attention, it was able to use high resolution feature maps. And since we were trying to detect very small objects, we needed to use a high resolution feature map in our model. To get it to adjust to our smaller data set, we needed to increase the speed of convergence. So we made some modifications for that. And we also need to be able to support a large number of queries. So to deal with the speed of convergence, we modified multi-scale deformable attention in the pixel decoder. And to support a large number of queries, we tried modifying the self-attention mechanism in the transformer decoder. So for regular deformable attention, just as a recap, we get a reference point and we're sampling different points anywhere on the image. However, because since we're detecting small objects, we wanted to only focus on nearby areas to the reference point. So to do that, we used a focused deformable attention where we go ahead and restrict the area in which deformable attention can take place. So with regular multi-scale deformable attention, we take our reference point and we're going to apply an offset to get some point somewhere on the feature map. But with our focused multi-scale deformable attention, we were hoping by restricting the area to a limited range, we would only focus on features that were relevant to small cells. And this would avoid long training times where we're paying attention to features far away and we slowly have to learn to look closer. So to implement this, we simply apply a scalar function, a scalar focus variable that controls the width of the box that we can access. And then also, because this delta p comes from a linear function, it's unbounded. So we needed to restrict it, otherwise scaling an unbounded variable would not do anything. So to bound it, we create delta O, and we simply do that by passing the query function through a linear layer and then bounding it between -1 and 1 using the tanh function. And this ensures that we get a nice box. We also needed to deal with a large number of queries since we had a large, since the average image had around 700 cells. So as the method we tried to implement was a bucket approach where we break the image up into many segments. Here you can see we use 9 segments and we only perform self-attention within those regions. This comes with the downside of like queries located in the corner don't get calculated with self-attention with nearby, but this was a trade-off we had to make to support an enormous amount of queries. We expected to use around 2,500 queries to support 700 cells. So we had to make some trade-offs. However, with both of these implementations, we still couldn't get the mass deformer to converge and predict reasonable results. So in conclusion, the transformer that we tried a very, very small data set with high hopes, and it didn't work out as well. Transformers just don't perform very well on small objects, and especially with high number of objects that we had. The convolutional network just shows that it still serves a very important role, as you can see by the results from the mass RCNN. If we wanted to implement this and get more reasonable results, we need a much larger data set. However, the creation of the data set already was a very expensive process just to create 46 images. It required annotating 35,000 different cells by hand for us. So that creating thousands of samples would just be impossible. So biological vision problems such as this have a long way to go for transformers still.
Good afternoon, everyone. We are group E. Our group member is Sun Yang, and Rachel and Avril and me. Today, our project is hierarchy signature verify user Samuel transform neural network. And the purpose of this project is to build a visual model to verify whether it is a writer signature or this writer signature is a genius or fraudulent. Okay, here is a simple example. The left one is a genius writer signature, and the right one is a fraudulent writer signature. So our model is to distinguish the genuine signature from the fraudulent signature. And regarding the related work of signature verification, there are mainly three approaches in this field. The first one is VIT architecture. The second one is the swing transfer architecture, and the most popular in this task of signature verify is the singlet. Singlet is the convolutional sending network, and in our work in this project, we also use the Samuel network architecture, and here is the Samuel network architecture is consists of two sets of convolution layer in parallel, and the input, two sets of input as the input goes through this two set of convolution parallel process of this law of combination, and merge at a loss function to compute the distinction of these two layers. Pass to the member user.
Go over the next part. So if you could stop sharing. The rest of the related work is in the paper, so we won't go over it too much. So I'll just skip to the methodology that we're doing. So we start with the data pre-processing. So we have an example of the two types of images we'll see, a genuine signature and a forged signature. So we're going to resize the images, and we're going to invert and normalize the images, and we're going to create the pairs of images. And so a pair would be a genuine and forged, two images paired together, and then another pair would be a genuine paired together. There wouldn't be a forged pair. And our largest data set has 160 different signatures. So, well, there'll be multiple of each type, but 160 different people. So that's why our data is constrained. And we went over most of this last time, but we invert and normalize the images because most of the image is white space. So this is our architecture we're using. So it's similar to the Signet architecture we saw earlier, but instead the input is directly an image in Signet, but this time we're going to convert the image into patches and add the embedding, which is needed for the transformer. And we replace the convolutional layers with the transformer encoder. And each image pair, so you feed one image through the entire process on its own. It has its own features. And then once you get the classification from the feature, you get two different classification probabilities for each image, or one for each image. And then you're going to, the output of the model will be the Euclidean distance between those. So if you have one classification probability vector and then another one, and then you do the distance between those two. So index one would be the Euclidean distance between index one of image one's output and index one of image two's output. And then that goes to, and then the loss function we're using to train is contrastive loss, which Shen Yang will go over.
Shen Yang, unmute your mic.
Sorry about that, I forgot to unmute. Yeah, so I'd like to describe the loss functions here. So here you can see for this loss function, we have three inputs. For x1 and x2 are the two input images. For y is a number to describe if it's genuine pair or genuine forged pair. So for genuine pair, y is 1. For genuine forged pair, y is 0. So here for the other parts, alpha, beta, and m here in this function are set to 1 in this SIGNET paper we are used. And for the dw, this dw is the Euclidean distance. Of course, for this contrastive loss, we could use other distance, but still, we just do the same thing as in the SIGNET paper. So we just use Euclidean distance. There are some alternative variants. Here in SIGNET, they just use 2 inputs, but for some other papers, they could use triplet loss or quadruplet loss, which means for triplet loss, we just use 2 genuine and 1 forged images as input. For quadruplet loss, we use 2 genuine and 2 forged images as the inputs. So it's based on the inputs. Here we only use 2 images as inputs. So here are some experiments numbers we use. For VIT, we use learning rate as 0.005. For string, we use learning rate as 0.001. And for both VIT and string, we just train our model with 20 epochs. The number of samples is 276. The batch size is 69, where the weight decay is 0.001 and clean the norm is 0.1. For the structure, we don't really change the parameters or the structures for the original VIT and swing. And we use 4 RTX Titan X graphic card to train our model. Here, to save our time, we just adapt the codes from the implementation in the Kera's official website. But here we don't just use them directly. Actually, we just use the last layer to create embeddings for our CME structure, and then use the two embeddings to calculate the similarity using Euclidean distance. So here, after we get the Euclidean distance, we cannot directly use it because here we want to know if it's a genuine pair or a genuine forged pair. So here we need to have a threshold to decide if it's a genuine pair or genuine forged pair. So here, if the distance is smaller than or equal to this threshold, we will consider it as genuine pair. And if the distance is larger than the threshold, we will consider it as genuine forged pair. So here, we just try out all different numbers for this threshold, and then we just use a threshold which can get the highest accuracy for our model here. So that's all the experiment details. Avrop will just discuss about the results here.
Can you see my screen?
Yeah.
Okay. So for the training part, the C accuracy for the model in CNN is 86 and 84 for the Bengali and Hindi dataset. And for VIT, it's 50% And for SWIN, it's increased like 20% more than VIT. It's 71% and 72% respectively. So the training time for VIT is around 2.5 hours, and for training time for SWIN is around 1 hour. So this like reduced accuracy happened because the transform is a data hungry model, though it's performed better than like CNN, but it's a data hungry, but our data set is pretty small. So and also like SWIN introduces inductive biases for locality and hierarchical feature representation. Also, it is translation invariance. That's why SWIN performs better than VIT in this case. And to remove this, to counteract this problem, we have some feature of like to like increase the data set. We are going to like improve like a data augmentation and use the BEIG transformer to generate better embeddings because like this is an image classification problem, and BEIG performs better than any other transformer. And probably we'll be using CNN as in a backbone and test different distance and loss functions such as like cosine distance and like triplet loss function. And we'll try to apply another CV tasks like face recognition, image retrieval, and anomaly detection. And this is all our references.